students, today our topic is RTL and micro-operations. So these are the contents of our today lectures. The register transfer language, register transfer, micro-operations, arithmetic micro-operation, logic micro-operation and shift micro-operations. So there is the brief introductions about register transfer, language and operations. As we know, a digital computer system exhibits an interconnection of digital modules such as registers, decoder, arithmetic elements and control unit. These digital modules are interconnected with some common data and control path to form a complete digital system. Digital modules are best defined by the registers and operations that are performed on the data stored in register. So we can say that the operations performed on data stored in a registers are called as micro operations. Now then what is the register transfer language? The register transfer language is basically a symbolic representation used to specify the sequence of micro operations. In a computer system, a data transfer takes place between processor registers, memory and between processor registers and input-output system. Now, what is the register transfer? Basically, the term register transfer refers to the availability of hardware logic circuit that can perform a given micro-operations and transfer the results of operations to the same or another register is known as a register transfer. Most of the standards notations used for specify the operations on various registers are stated below. Now, MAR are basically used for denote the memory register, memory address register, and it is designed by the MAR. Similarly, PC denotes the program counter register and it holds the next instruction's address. And IR basically denotes the instruction register and it holds the instructions being executed. Now, except these, we basically denote by the capital letters the register processor registers. We can also indicate individual bits by placing them in parentheses. For example, PC is a program counter register and in this parenthesis we are denoting the bits used by the program counter. And similarly R denoted here 0 to 15. It means R is a processor register which have the 16 bit. And next, the data transfer from one register to another register is represented in symbolic form by means of replacement operator. For instance, the following statements denote a transfer of the data of register R1 into register R2. Now, what's the micro-operations? We know that simple digital systems are characterized in terms of a register and operation. The register they contain and the operation that they perform. So these two things are very compulsory for characterize a digital systems. The operations on data in registers are called micro operations. The functions built into the registers are example of micro operations. For example, here shift, load, clear and increments of functions are basically known as a micro operation functions. There are basically four types of the micro operations. First one is register transfer micro operation. Second is arithmetic micro operation. Third is logic micro operation. And fourth is shift micro operation. So what is the register transfer? So basically we know here what is the register transfer operation. So basically we now copying the content of one register to the another register is known as a register transfer. A register transfer is basically indicated as given a statement like we mentioned here. R1 denote the register R1. So this statement says the content of register R1 is basically transfer into the register R2. So we can say that is the register transfer micro operation, and it is also known in shortly like as a micro operation. A similar transfer of the bits from the source register R1 to destination register R2 during one clock of plus, and basically this transfer is performed like as a parallel way. So next one is arithmetic micro-operations. There are basically four types of arithmetic micro-operations: addition, subtraction, increment and decrements. And except these operations, there are some additional arithmetic micro-operations like as a add with carry, subtract with borrow and transfer load operations. Now here are some example of arithmetic micro-operations. Here first statement denote the content of register R1 plus R2 is shifted or transferred into the register R3. In statement second, we observe that content of register R1 minus R2 is transferred in the register R3. In statement third, we observe that complement of register R2 is transferred in register R2. So shortly we can say there is a complement of content of R2. And in statement fourth, complement R2 plus 1, that is also known as the 2's complements of a binary bits, because a register mostly have the binary stream. So R2 plus 1, it means 2's complements of R2 is transfer again R2. Here we denote R1 plus complement of R2 plus 1. So as we know that R2 complement of R2 plus 1 always denote the negation of R2. So we can say that it is basically subtraction micro operation. So R1 minus content of R1 minus R2 is again subtracted in register R3. Now in statement 6, R1 plus 1 is shifted in R1, it means that is the increment micro operation, and in last operation we observe that content of R1 minus 1 is shifted into R1, that is denote the decrement micro operation. Now except of this, we are going to design a 4-bit arithmetic circuit which can perform all arithmetic operations. So to design a 4-bit arithmetic circuit, because that is a 4-bit, why we call this circuit like a 4-bit? Because it produces 4-bit output. So due to this, it is now a 4-bit arithmetic circuit. Now here there are basically two control line S0 and S1, and there are two input register A and B. So these control lines, basically these control lines are used to select the input lines of multiplexer one by one. So using these two selecting lines, we can control the 4 input lines of a multiplexer. So due to this reason, this multiplexer is also known as a 4x1 multiplexer, because we know the principle of the multiplexer work multiple input one output. So there are number of input are 4 and output produced by output from the by the multiplexer is 1. Due to this reason, it is known 4x1 multiplexer. And next combination is here full adder, and we know that a full adder basically have the 3 inputs. So we can observe here one input is given by Cin, that is C0, and next input is given by the contents of register A, and third input is given by the output of the multiplexer. So there are basically three input and there are two output. One output denote D0 and next output, that is the C1. So we can observe that in each full adder there are three inputs and four output. Now we observe the two tables of 4-bit arithmetic circuit, how it works on the values of the selecting lines and input carry C. Now we observe these two tables. If both selecting lines inputs are 0, 0 and carry in is 0, then we get the output at the Y terminal. It means output of the multiplexer we obtains B, and actual output after processing through the full adder, that is denote at D terminal, we obtain A plus B. So we can say that is the micro operation of addition micro operation. Similarly, when both input are 0 and input carry is 1, then in this case we get the Y terminal B, and at D terminal we obtain A plus B plus 1. So we can say that this micro operation is add with carry operation. Next, when we take the selecting line S10 and S01 and selecting input is 0, in this case we obtain at the Y terminal complement of B, and at D terminal we obtain A plus complement of B. So we can say this micro operation is basically subtractions with bar. And similarly, when we take it input carry 1, then in this case we obtain Y terminal complement of B, and D terminal we obtain A plus complement of B plus 1. That is basically known as a subtraction operation, because complement of B plus 1 denote the negation of B. So here become A minus B. So that is the subtraction operation. Now in here we take selecting lines S10 and S00 and C input is 0. In this case Y terminal we get the 0 bits. So and D terminal we obtain the all bits of A. So we can say at the output terminal we obtaining all the contents of the register A. So we can say in terms of the micro operations, transfer of A, it means all bits of A are transferred at the output terminal. Similarly, in case of S1 and S0 and C in 1, in this case we obtained at Y terminal all bits 0 and output terminal we obtained A plus 1. So that denotes the increment operations or increment micro operation. Now here we obtain all control lines C1 and C0 is 1 1 and C carry is 0. In this case we get at Y terminals all bits, so Y terminal bits 1, and in this case at output terminal we obtain A minus 1, that is denote the decrement operations. And at last, when all inputs are 1 1 and C in 0, in this case we obtains the Y terminal at once and at D terminal we obtain A. So that denote the transfer of content register A. So that is denote the actual operations performed in 4-bit arithmetic circuit. Because this all operation we can perform using this circuit, due to this reason it is known as a arithmetic micro-operation circuit. Now next is logical micro-operations. Logical micro-operations are those micro-operations which are performed using the logic gates concept. So, to specify binary operations on the string or on the bit in a register, the logical micro-operations are basically bitwise operations. They work on the individual bits of data. So, we can take the example of the micro-operation like AND, or AND gate, OR gate. It means all operations which are performed through the logical gates, and or XOR, complement and NOT is considered like as a logical micro-operations. Now, here is a circuit diagram how logical micro-operations do works. So, that denote the logical diagram, logical circuits of logical micro-operations, and that is the two table of logical micro-operation. So, as we know, the overall role is depend on these selecting lines. According the value of this selecting line, we obtains which operation will be performed. Now, we observe in two tables. If both inputs are 0, 0, then in this case, selecting lines, input line for multiplexer 0 is activated and all remaining lines become deactivated. So, in this case, output at 0 line is obtained from the AND gate. So, operation here is AND operation. So, he outputs A and P, and micro operation is AND operation. Similarly, when we take 0, 1, in this case, the multiplexers one line is selected and all remaining lines become deactivated. So, we obtain the output at line 1 is coming from which circuit. So, we observe here the OR gate. So, output become OR, and 1 0 in case of 1 0 we basically select the line 2. It means line 2 of multiplexer. So, we observe here line 2 from which logic gates we obtain the output. So, here XOR gate provide output at line 2. So, at 1 0 the micro operation is XOR, and in the case of 1 1 we obtain the complement of A, because in case of 1 1 we select vertically line 3rd, and in this line 3rd the output is coming, input is coming from the NAND NOT gate. So, due to this is now as a complement. Now, next is shift micro operations. So, there are shift micro operations are basically those operations which are used to shift the content of a register either left hand side or right hand side. So, we also can say the shift is again classified into right shift or left shift. So, there are basically three types of the shift micro operation: logical shift micro operation, circular shift micro operation, arithmetic shift micro operation. So, first we consider what is the shift micro operation. So, they are classified into right shift and left shift. In the right shift, the serial inputs are provided in the contents of a registers, and they are inserted from the they are moved from the right hand side. So, due to this reason it is known as a right shift micro operation, because these contents are shifted here, this here, this here, this here. And similarly, when contents are moved towards the left hand side, then we know that is the left shift micro operation. Next is logical shift micro operations. In a logical shift, the serial input to the shift is a 0 bit. It means when we shift the logical shift micro operation, then it also classified in left logical shift micro operation and right logical shift micro operation. So, if we perform the right shift micro operation, then In the case of the last bit is always inserted by the 0 bit, and similarly in the left the last bit always inserted with the 0 bit. So, when we use the logical shift micro operation, the following notations are used: SHL, that denote for the logical shift left, and SHR for logical shift right. So, here we also take an example of here. We are shifting the contents of register R2 the right hand side, and we are performing in the register R2. So, that is the after shifting the content of register R1, register R2, we again transfer it into the register R2. Next is the circular shift. In a circular shift, the serial input is bit that is shifted out of other end of the register. So, in the circular shift, we also can say that in this shifting, the MSB become the LSB, and sometimes LSB become the MSB, that depend the rotation of the shifting. In the register shift, in the register transfer language, the following notations is used. SIL basically used to denote the circular shift left, and SIR used for circular shift right. For example, we take here SIRR2, it means circular shift, circular right shift in register R2 is again after circulating again transfer in register R2. And similarly, SIL R3, it means circular left rotation in R3, and after rotation we again shift the content of R3 into R3. So, we also can say there is no any bit loss. We basically rotate the data in a register. So, here MSB, sometimes MSB become LSB and LSB become MSB. Now, next is arithmetic shift micro operation. Basically, this arithmetic shift micro operations are performed on the sign number. So, in the case of the sign number, it is very important to identify the sign of a given number. It means number is positive or a negative. So, in the arithmetic shift micro operations, the left arithmetic shift micro operations must be checked for the overflow, because in the case of the arithmetic shift micro operation, we always have to consider the sign. So, to check this overflow, we basically use a XOR gate at the MSB and previous bit of the MSB. So, in XOR gate, we take basically two input, first input from MSB and second input for pre-bits of the MSB. So, if both inputs are the same, in this case we observe basically overflow bit 0, and if both are different, in this case we basically obtain 1. So, there are some notation used in the arithmetic shift micro operation. First, ASHL, that is basically used to denote the arithmetic shift left, and SHRL is used for denote the arithmetic shift right. Here are some examples. ASHL R2, it means arithmetic shift left the content of register R2, and then we again transfer in register R2. And similarly, ASHR, it means arithmetic shift operation right in register R3, and after making rotation we again transfer it in register R3. So that is the circuit diagram, and this overflow bit V is basically used to identify the number is positive or negative. If there is no any change in this bit, then we can say that number is not make change in the sign. And if for example, if number is positive after rotation, so in basically for the positive number we denote here 0, and for negative number we denote here 1. So overall positive and negatives are observed from the output value of this XOR gate. So today our lecture is finished. Thank you.